Hello. I would like to talk with you today about the Principal Solar Institute PV Module Rating System. First of all, I'd like to explain why it is we created a PV module rating. The Principal Solar Institute was founded by Principal Solar Incorporated, and their primary business is the acquisition and operation of solar electric production facilities. And so one of the key elements in choosing a facility for acquisition is to understand how much energy that solar farm might produce over the course of its lifetime. I think it's absolutely essential for a utility operator to understand lifetime energy production because it is energy that's being sold to the consumers. Well, when we hit upon the idea of lifetime energy as a metric, it occurred to the Institute that any purchaser of PV modules could use the PV module rating to do their own cost-benefit analysis and compare PV modules. So, a little bit about lifetime energy production. At first, we at the Institute began to look at several different ways to try to assess PV modules, various subjective approaches and scorecard techniques. None of these seemed very satisfying until we landed upon the concept of lifetime energy production. Basically, by lifetime energy, we mean the quantity of energy that a PV module would produce in 25 years of operation. The graph at the right on this slide shows, in fact, that it's expected the PV module energy production can decline over time. And so what we're able to do is calculate a quantity of energy based on PV module characteristics, and we use a model of irradiance and temperatures to add up the energy production. So looking at public databases and information provided by the California Electric Commission and data sheets from manufacturers, we were able to identify 7 key characteristics of PV modules that affect the energy production. One of these is the actual maximum power versus the advertised power. So not every module is going to produce exactly what the manufacturer claims. In this case, what we mean by actual is the product of the voltage and current at maximum power under standard test conditions. We also use negative power tolerance. This further reduces the actual maximum power. We also look at the nominal operating cell temperature. These are published numbers that relate to the power and temperature characteristics of the PV modules, and we use the temperature coefficient at maximum power called gamma in order to make an assessment of the energy. There is also reduced electrical production at lower incident light, and one of the low power criteria for monitoring and assessing PV modules is the low light level, 200 watt per square meter incident power. And finally, total area efficiency. This is where we bring total area, this is where we bring efficiency into the PV module rating. As we all know, efficiency is very important for energy production, and we calculate this by taking the energy produced and we divide by the module area, and then the annual power reduction. Instead of using some accelerated testing methodologies to try to come up with a trustworthy annual power reduction number, we put the onus on the manufacturer's warranty, and we calculate the annual power reduction based on what the manufacturers say will be remaining at the end of their warranty, typically a 25-year warranty. So what do we do with these characteristics? Well, we use them to model the lifetime energy production. PV module characteristics that affect this production, this energy production, depend on irradiance and temperature. So you can see that we have a very simple model in our phase 1 model of irradiance and of temperature. We've tried to pick, for our first models here, some very simple things that seem to sample fairly well the range of values that might be expected for the PV modules to be operating under. So what we do is we create a comparative rating by calculating the impact of energy on each PV module hourly through our model of a radius and temperature over a 25-year period. And that's how we come up with a lifetime energy. That lifetime energy result we take and we divide it by the lifetime energy of what we consider to be an ideal PV module. So the PSI rating is a ratio. It's the calculated module lifetime energy production divided by the calculated ideal module lifetime energy production. So the rating is a comprehensive metric for comparing the energy performance of PV modules. Now, we realize, of course, that our first model was fairly simplistic, and we have plans to develop a model that takes location and temperature into account. So I've got a graph here on the left that shows representative data from a location near Buckeye, Arizona, and the irradiance throughout a day, June 1st as opposed to December 1st. And you can see that, you can imagine that there would be ranges in between those two curves for the available sunlight at that location. In the graph on the right, I've plotted the December daily temperature range. So with a more sophisticated model, we would be able to show in a comparative way how PV modules' performance is affected by region. Still, the PV module rating would be a comparative score. You would not get a result out like the number of hours, kilowatt hours of energy produced, but you would be able to compare one module against the other in a relative way and say module A, module B, which one produced greater energy over its lifetime. So the PSI rating is probably most useful as a side-by-side comparison of energy production performance. It's a performance metric, and because of the way we have used the ideal module energy production to normalize the score, you can say whether side-by-side tests of PV modules at the same location would show a difference in the power production, the energy production. Now, just because we have the rating number doesn't tell the whole story, and we don't think that it, we don't expect people to take the PSI rating as a reason for choosing a module, because there are many other reasons why you might have to choose a PV module. Manufacturer's financial strength, pricing, delivery, reliability, other integrated system components, and even regional differences are factors that must be considered before you select the best PV module. But at least with the PV module rating we provide, you have a basis for a cost-benefit analysis and a basis for comparing modules side by side. So, ranking and rating the PV modules. The Principal Solar Institute web pages provide a table of the PV module ratings. There's other data that we provide on these web pages, and if you'll visit our website, you'll see that there are two classifications that we present. The crystalline, that includes polycrystalline and monocrystalline, and all the others, which we put into the thin film category. So those are on two separate pages. Now, the column on the left on these pages shows the rank, modules by model number, which one is highest in terms of PSI rating and descending order of rank. We also present the PSI PV module rating number. That's next to the column that also has a percentile rank. Now, percentile is not the same thing as rank, and we get this question a lot. Percentile is the standing of a PV module within the distribution of all 10,000 modules that we have in our database. So when you look at, for example, the crystalline PV module webpage, you'll see that there's only 500 PV modules listed. We truncated the list at the top 5% to save on page load time. If anybody doesn't see a PV module that they would like to know the PSI rating or the ranking of, they can contact us through our web interface, and we will look those up in our database and send the numbers out. So, in conclusion, the PSI PV Module Rating is a comparative score based on lifetime energy production. It's important that I want you all to understand that we do not currently test PV modules, but we use test data that is publicly available. We are developing a model that uses regional conditions, and we're working to develop interactions with university, industry, and government people. We welcome feedback and suggestions through our website, www.principalsolarinstitute.org. And thank you for your time.
Thank you, Matt. Again, if you have any questions from the audience, please chat those. You can send them to all panelists through your chat window in the lower right corner. I'm going to save those questions for the end, though, as they come in. We want to go ahead and make sure we have time for the three presenters. The next presentation was prepared by Ken Allen. Again, Ken was the COO of Principal Solar. Part of his job was to use selection criteria to determine which panels Principal Solar should acquire for projects under development, and also to evaluate the value of existing projects. So these slides will be presented by Matt. So now I'll hand it back over to Matt.
All right, thank you, Rick. So Ken is instrumental in the acquisition process at Principal Solar Incorporated, and he does a lot of the site visits to do the assessment of the PV modules and the other equipment there at the solar farms. And so I asked him to put this presentation together to give some examples of how the PV module rating could be used, and in fact is used by Principal Solar. A couple of simple examples. First of all, the example he calls direct comparison. So one of the things that I found surprises people is that the nameplate rating of PV modules does not provide the detailed information needed to differentiate between those modules. For example, here are two PV modules that I selected from our ratings. Let's call them Module A and Module B. I've concealed the model numbers because we're not trying to promote any PV module manufacturers here. Well, both of these PV modules are polycrystalline. They both have a nameplate rating of 275 watts. But it turns out they have different PSI ratings when calculated through our lifetime energy production models. So if you look at the ratio, you'll see that the lifetime energy production from Module A is 110% that of Module B. So that's a 10% difference between modules that have the same nameplate rating. Now, some people might think a 10% difference is small, but to a utility operator who's got razor-thin margins, a 10% difference is something worth noting. Again, just looking at the rating numbers doesn't tell the whole story. It's important to look at cost and cost-benefit analysis. And so the next example, we look at the cost-benefit analysis in a small project in terms of energy cost comparison. So again, I selected two modules, Module A and Module B. This time, however, one of them is polycrystalline, and Module B is monocrystalline. They have two different power ratings, and of course, two different PSI ratings. Now let's say that you happen to know that Module A can be purchased for $1 a watt, and Module B is only 90 cents a watt. Well, to reach a 2 kilowatt project size, you'd have to buy 10 modules of type B or only 8 of type A, and you can see their associated costs. So in fact, you end up spending less for the lower cost module, even though you have to buy more. Now, following the previous example, you can see that the lifetime production of Module A is in fact 126% of what Module B will produce. This is a substantial difference. In fact, it's a great enough difference that it will swing the analysis on lifetime energy cost. You see that even though B is more cost-effective to install, the cost of the electricity produced per kilowatt hour is going to be 113% of the cost of A, so a 13% difference. So in this example, I think it's really illustrative of the kind of power of the PV module rating. You can see a lower upfront cost, but it yields a higher cost of energy produced. So in conclusion, a couple of examples. The PV module rating is a comprehensive comparative metric based on lifetime energy production. It's a true performance metric, unlike just using a nameplate wattage rating. And it allows for a quantified cost-benefit analysis. Now, I'm sure that there are more examples and ways to use the PSI rating. I've just given a couple, and we've thought of others. I'd appreciate hearing from people who think of other ways to use the PSI rating, because we would like to understand what other people might see that would be useful in this. So please contact us through our website interface online.
Okay, thanks, Matt. And again, if you have any questions, chat those in the lower right corner. Send to all panelists. I'll save them for the end. The next half of our presentation will be Steve Hegedus at the Institute of Energy Conversion. He's going to be speaking about the performance comparison of reported field data from different PV module technologies. And I will now pass the presenter control to Steve. Steve, go ahead and begin.
Okay, thank you. Yes, I'm at the Institute of Energy Conversion at the University of Delaware. This is the outline of what I'll be talking about today. First, because the IEC is not very well known maybe to the community that I'm talking to, I'm going to just give a little introduction about what we're about. And I'm going to be then talking mostly about the metric of kilowatt hours per kilowatt installed, or STC, and why it's an important metric. What are some critical issues both in determining the numerator, the kilowatt hours produced, and the kilowatts installed, the denominator, and then giving some examples and interpreting them in terms of the temperature coefficient of the efficiency, the low light efficiency, and most importantly, variables of the measurement, the actual initial characterization of the wattage of the PV module. So the Institute of Energy Conversion, IEC, was founded 40 years ago. We had our 40th anniversary this year to perform thin film PV research, and we are the world's oldest continuously operating solar PV research facility. We sort of made our name when we made the first 10% efficient thin film solar cell in 1980, and there's a picture of it there. It was a flexible cell made on a roll-to-roll process. We were designated a Center of Excellence by Department of Energy in '92. We are part of the University of Delaware. I'm a university employee, but we are soft-funded. We support ourselves through government and industry contracts. We have over 20 deposition systems. We can make a wide range of different types of solar cells, both growing the films, fabricating the devices, and characterizing them. And that lists our staffing right now, and we do both fundamental science, engineering, technology transfer, and workforce supply. And the other pictures are the top one's a piece of equipment here, a multi-chamber plasma CVD system for depositing amorphous silicon, and then the bottom picture is a 4x4-inch monolithically integrated copper indium gallium diselenide mini module that we made. So our key technology thrust areas are the copper indium gallium diselenide-based polycrystalline thin film cells, and there we're looking at alloying and roll-to-roll versus glass. We also have extensive experience with polycrystalline cadmium thin film solar cells like First Solar makes. We work on a range of silicon-based solar cells, front and back heterojunction type devices. We were the first to make and propose the heterojunction IBC cell, where we sort of merge the Sanyo hit cell approach and the SunPower back contact approach, take the best of both and integrate them into a device. We also do some reliability and stability studies, and we have a unique facility for doing damp heat testing under both voltage and light bias to try to give an additional reality factor to the standard damp heat tests so that the cells are also seeing illumination and electric field. And we have some inline monitoring and device imaging mapping facilities. So, why is this kilowatt hour per kilowatt useful as a metric? Well, if you look at the numerator, kilowatt hours, that's the energy produced over time. It might be over a year, or it might be over, as Matt was saying, over the 25-year period that you would expect to have a facility in operation. And it's directly related to how much somebody expects to be paid, whether it's for a power purchase agreement or some other kind of contract, or if it's a residential or commercial system, how much are they going to save on their electric bill? And it necessarily includes all these sort of vague and somewhat imprecise factors: the weather, the amount of sunlight, degradation, shading that might occur only seasonally or daily, dust accumulation, which is a big deal in some areas, and seasonal annealing. So all these things are temporal and vary. Then you've got the denominator, which is the rating, the power rating of the module. Now, at first glance, you'd think, well, that's a pretty basic parameter, right? I mean, somebody sells you a module and says it's a 250-watt module, so that's what its rating must be. Well, yes, that's how much you paid for the module, because typically, you're going to buy it based, on the dollars per watt rating. And all modules are rated under what's called the standard test conditions, which are universally applied. 1 kilowatt per meter squared, which is called 1 sun, 25-degree module temperature, not air temperature, but the actual module temperature, and a specific illumination spectra, it's called air mass 1.5. Those three conditions together are called the standard test conditions. All modules are rated under them, and they may occur as much as a few minutes a year in every location, which means that the whole rest of the time your modules are being exposed to typically lower light intensity, higher temperatures, and bluer or redder spectra. And in fact, as I'll sort of give you what my conclusion is, looking at a number of reports, one of the largest sources of uncertainty in kilowatt hour per kilowatt metric is in establishing what is the initial kilowatt rating of the module or of the array. Continuing with this idea, this parameter, kilowatt hours per kilowatt, if you look at it, the kilowatts cancel out and you're left with essentially units of hours. And so what this measurement is, it's equivalent to the number of hours per year or over 25 years that the array was acting as though it was producing under its rated STC power. Oftentimes in the literature, you'll see this parameter referred to as Y sub F, the final yield, and it can be AC or DC, and you should be aware that if it's AC, after the inverter, it accounts for the inverter efficiency and the fact that the inverter efficiency will be a function of light intensity as well. And just to give you an idea, some typical numbers, if you assume you're in a place that has equivalent of average of 5 hours of sunlight per day over the year, and you have 20% system losses and module losses, then you multiply those together and you come out with a module that should produce on average 1,460 kilowatt hours per kilowatt per year. Just as an example of how you could, what sort of numbers we're looking at for that. So because my lab is very much interested in technology development and particularly looking at thin film technologies, it's been widely reported for over 2 decades that thin film modules will have a higher kilowatt hour per kilowatt performance compared to standard crystalline silicon. And that's not surprising. It's consistent with some very fundamental physical principles that are different between thin film solar cells and crystalline silicon, but the magnitude of what was reported was just too big. It was so large that many people were suspicious of it. And the most obvious difference between the thin films and the modules and crystalline silicon is the temperature coefficient of efficiency, which Matt alluded to as one of the parameters that they include in their modeling. I refer to it here as TCE, temperature coefficient of efficiency. Thin film, it's always negative, which means module performance always goes down as the module heats up, but thin film modules decrease less. In other words, they have relatively better high temperature performance than a crystalline silicon module. Now, it's really not fair to lump together all thin films because there's different materials, different processes, different device structures, and some authors do that, and it's really not fair because they are different and they do have different parameters. But also recently, some of the new high-efficiency advanced crystalline silicon device structures, like the HIT cell from Sanyo and the back contact cell from SunPower, also have lower temperature coefficients than standard crystalline silicon. And so they also fall into this area where they might be expected to have, and in fact have been shown to have, higher kilowatt-hour performance. So I was asked to write a review looking at published data, comparing thin film and crystalline silicon module field data for a new journal, Wiley Journal, and the abstract is at the end of this talk, but I'm going to be including some of the information that I presented in that paper here today. So this slide shows a graph that I made showing data from 3 different European cities, Mallorca in Spain, a sunny, hot climate, Lugano, Switzerland, sort of a moderate, sunny, cooler climate, and then finally Oxford in England, a cloudier, cooler, the coolest climate. And the bar chart shows the data broken up by technology, monocrystalline, multicrystalline, amorphous silicon, all different configurations, all different flavors, single, double, or triple junction, and then CIGS. And I grouped all the modules together by technology. So, you know, if there were 4 different monocrystalline, I just lumped them all together for each site. But what you can see are very consistent trends as you go from the y-axis is the kilowatt hour per kilowatt that was reported. And as you go from Mallorca to Lugano to Oxford, from green to blue to red, you see a steady decrease in every technology in the output. Well, that's to be expected because of the hourly sun hours. Then if you go from technology, you see that, well, the 2 crystalline silicon or mono and multi-silicon technologies are pretty similar in both locations. But then when you go to the 2 thin films, things jump up. And in fact, both the amorphous silicon and the CIGS have, on average, 16 to 20% higher kilowatt-hour performance in all 3 locations. And like I said, these values have been, you know, widely referenced and quoted. They were done by reputable groups, but the magnitude is just a little bit too big to be believable. But this is the data that was out there and that there were other reports too, but I just selected these. So this slide shows some of the groups and organizations that publish data that I found especially helpful. And if you're interested in looking at comparing different technologies, you might look at some of these studies. The best thing for you to do would be to get a copy of my paper. I have about 50 references in it, including many different groups that have compared different technologies in the same location or in different locations. The 2 that I'll be using today, primarily the first 2, one was a group study done jointly by the University of Cyprus and University of Stuttgart, where they compared 13 different module technologies in those 2 locations. And they wrote a lot of papers over looking at the final yield, degradation, the effect of measurement detectors, characterization, rating issues, and I'll be showing you some of their data later. And then also there's a consultant, Steve Ransom, who's based in England, and he has access to a lot of data, and he publishes papers in IEEE and European PV conferences looking at the uncertainty, variability, comparing different models, comparing the effect of weather conditions on different module output, looking at different technologies and orientations. And then there was others in other locations. Since if you're U.S.-based, I'll mention Arizona is very well represented, probably the best represented place in the country. Both the major utilities there, APS and TEP, have produced several papers where they look at, from a utility perspective, large systems ranging up to 3.5 megawatts, looking at O&M costs, final yield, degradation over time, comparing fixed versus one-axis, two-axis tracking, quite a wealth of information. And since they're a utility, they really don't have, a bias one way or another with any technology. So those papers are quite useful. Okay, this slide shows on the left data of the final yield versus efficiency from the city of Hokuto in Japan, monitored over 2 years. And each symbol represents different technologies, which again I lumped together. The monocrystalline modules are represented by the black circles. And you look in the blue multicrystalline and the black monosilicon, those are the most mature technologies that we have. And yet look at the wide range of yield that's reported for them. It varies by almost 20%. And yet they have all about the same initial efficiency, and since you generally pay for modules based on their initial performance, you would be getting paying similar amounts and getting widely varying yield or production from those modules. And then the thin film modules that are represented consisted of amorphous silicon single or double junction and CIGS. And then I'll point out that way off on the right at 18 or 16% efficiency was the HIT or hit cell technology arrays, and those you would have expected to be much higher, and you would have also expected the crystalline, the green amorphous silicon to have been higher based on physics, and you see that they weren't. So that's sort of indicating that there's some stuff going on here that may not be just as simple as applying the basic physics that we think that we know. And then over on the right is data from the group in Nicosia, Cyprus, over 2 years, showing similar technologies. Here you see that the HIT cells did quite a bit better, and the best was the IBC cell from SunPower. The CAD Telluride module in blue, or array, should have been much better, again, based on its temperature coefficients and stuff, and yet you see it sort of was mid-range. So again, this is data telling us that what we'd expect doesn't always occur in reality. So, people, they dug much deeper, and if you read their papers, you can find out some explanations for some of this discrepancy. So, one of the things about modules is that, yes, we all know that as the amount of sunlight on them decreases, the amount of power output is going to go down approximately linearly, and that's the first-order effect. But there's a number of second-order effects that add up to several percent, maybe up to 5 or 6 or 7%. And as one of the speakers said earlier, that's a lot to a utility in terms of differences in performance. And all of these are what I would call second-order effects, and they are all due to the way in which the module responds to other meteorological conditions. So what happens when clouds or humidity, reduce the incident sunlight on a module? Well, of course, the output goes down, like I said, linearly. But other things happen. For example, you have less light on the module, so it's going to be cooler, and therefore you'll have less temperature-related losses. With less light, you have less current, you're going to have less I²R power losses. Haze and clouds give you more scattered light, you're going to have more indirect light, and that could either add or subtract to your module efficiency, depending on sort of how it's designed. More scattered light means the spectra shifts to the blue, which is an advantage for cells that have higher band gap or let's say higher blue response. And all of these changes, all of those ones other than the first order effect are off, except for temperature. I'm sorry, I should say except for temperature. All of them are lumped together in this parameter that Matt mentioned as the low light efficiency, and it's the ratio of the efficiency at 200 watts divided by 1,000 watts. So it's the efficiency of the module at very low light intensity. This data I obtained or extracted from a paper published in a conference last year, and what it does is it compares the benefit or the gain expected for a typical thin film module that has the better temperature coefficient, and namely smaller, and a better low light efficiency compared to crystalline silicon for two different locations. So the green bar is the low light the gain in low light efficiency. So in Munich, which tends to be cloudier, the thin film module and you can see the parameters there, the low light efficiency of the thin film module here was slightly greater than 1, and the crystalline silicon module was slightly less than 1. So in Munich, the thin film module would do better primarily because of the low light efficiency, whereas the difference in temperature coefficient, not so much, because it doesn't get very hot there. In contrast, in Albuquerque, where they have a lot of direct sunlight all year, the effect of the low light efficiency isn't so big, but the temperature coefficient is where you get the primary gain. So when you add the two together, it turns out that in either location, the thin film module would outproduce the crystalline silicon by, let's say, 5 to 6%. And that is very consistent with what is reported from most of the recent large area, sort of utility scale installations where people have been comparing thin film cadmium, who has parameters very similar to the ones that I listed here, to crystalline silicon modules. So on the order of 5 to 6% can be justified based on known parameters of the thin film modules in terms of temperature and low light efficiencies, not the 15 to 20% that was seen in some of those earlier studies. So there's a lot of uncertainty, though, in these numbers. If we're going to say that that 5% number that I just calculated is meaningful, that assumes that we can determine the initial performance and the measured kilowatt-hour performance to better than that sort of number. So when you look at the kilowatts rated power, there's quite a wide range of powers, and so typically a module manufacturer might sell modules at 240, 260, 280 watts, or maybe 280, 290, 300. But they're going to bin them, and there's going to be a range. So if you buy a 250 watt module, it could be between 245 and 255. Okay, so that's like a 3% plus or minus 3% variation. Similarly, the best that we expect to get from flash testing of individual modules with a well-calibrated system, with a calibrated module, is on the order of plus or minus 2% for crystalline silicon, and the very best you could expect for thin film is probably going to be on the order of 3%. And that's because there's some stabilization or pre-biasing steps that are required by the IEC standards. That's not my IEC, that's the International Electrotechnical Commission. For the thin film modules, that before they're tested, they should go through this brief regime of stabilization or light soaking. Now, if you look at irradiance, then you've got you're monitoring the outdoor test illumination at your installation site. The best you can do with pyranometers is about plus or minus 2% with annual calibration. And if you're comparing two locations that have different, even if it's the same brand of detector in two different locations, you're now looking at a plus or minus 4% variation in the annual irradiance at those two locations. And then different detectors can maybe accumulate dust, or they'll have differently than the modules that you're measuring, or they have different temperature sensitivity than the module you're testing, or maybe they're shaded differently. So you can now get differences between the detector and the actual illumination on the module itself. So that adds additional uncertainty in the measurement. And if they use a different type of detector, like a silicon detector, which has more sensitivity to spectral, the sky spectrum and temperature, but they're cheaper, you can now increase these uncertainties even more. So you start looking at these numbers and you realize that there's, on the order of, 5, best you can do would be maybe 5% between locations, and without much effort at all, you could be looking at plus or minus 10%. And that's what a number of people have concluded about comparing results from different sites. So this is data from the study that was done between the University of Stuttgart and Cyprus. This graph was, I cited there, was published in 2010, and this shows the yield, the kilowatt hours per kilowatt for 12 different technologies installed in the 2 different locations. The purple data is in Cyprus, the sunny location, so it has a higher kilowatt hour production, and the green is in Stuttgart. And the technologies are broken down between monocrystalline, multicrystalline, and then they've lumped together the thin films, and you'll see what all those are in the next slide. But if you look at them, you see an average over on the right, for example, in 1570 kilowatt hours per kilowatt was the average, but to try to draw meaningful distinctions between them and say, is one module better than the others, you look at the error bars there and you see that, first of all, the error bars certainly straddle any difference between the modules in either location, and also in particular the thin films have much bigger error bars associated with them than the crystalline silicon, although even with the crystalline silicon some of them are significant. The error bars are larger than the difference between any of the technologies. The error bars arise from uncertainty that I mentioned before in terms of the binning, because these are using the rated power, the manufacturer's rated power that you would have paid for that module. You know, if it was rated as a 250 watt module, whatever it was, you were paying for it as though it was a 250 watt module. Now, the next slide shows that data on the right, on the top, where each of those 3 figures now are, the difference between them is how the denominator was determined, namely how the power, the STC power of each of those module arrays was determined. The top one is the one I just showed you. That's where they used the manufacturer's rated data. The middle one is where then they used actual flash test data that they made on each individual module that they received. Actually, it was done at an official testing lab. So that's where, and now you see what happens to the error bars. They get much smaller. So they eliminate the binning error and the uncertainty in the manufacturer's testing, and now they know what was the actual kilowatt installed for each module. And you'll notice that, yes, the error bars get smaller in both locations, but still any differences between the technologies are within the error bars themselves. So there's no meaningful distinction. And you can see in the table that I put there, for example, with them using the manufacturer's rating, the kilowatt hour per kilowatt ranged from the lowest to the highest by 18%, but the uncertainties were plus or minus 18%. If you go to the flash testing, the uncertainty or the range goes down to 12%, but the uncertainty is still plus or minus 8%, so greater than the range of data. The third one is where they measured the power over a period of several months or a year in the field as they were installed under conditions that approached STC and determined a net power rating for each of those arrays. Now, the error bars are much smaller, and as you can see from the circle that I drew there, they highlight that the thin film modules do actually outproduce in a meaningful way, meaning more than the error bars, the other array technologies that are shown. So as you go through this progression, it's a lot of work to do this, but if you really want to be able to evaluate the performance of a system and determine how it's performing, and this, is true for not just the module performance, but this takes into account everything else, because the inverters, because these are all AC data. So you've got other factors built in there, but all that's being done going from the top graph to the middle to the bottom is changing the denominator of that ratio of the kilowatt hours per kilowatt. So they're changing how the module initial performance was evaluated. There's still, as you can see, a remaining error bars, and that's partly the error bars due to the initial rating, but also, like I said, in evaluating the kilowatt hour performance, because you've got uncertainties in your detector, your illumination detectors, and in your other aspects of the energy conversion. So you're never going to totally eliminate and get the uncertainty, but you can certainly go through steps that help you to minimize it. And when you do, differences in technology or installation can pop out, as you can see in that bottom graph. In summary, comparison of field data is complicated. There's uncertainty in the module ratings and in the irradiance measurements. Experts who've looked at this in detail estimate that at best you can get about a plus or minus 5% uncertainty at the same location. Now, that's, for example, if you're comparing technologies installed at the same location. If you want to be comparing different locations, you get larger uncertainty due to the differences in detector calibration, module rating procedures, and how those modules respond to the weather conditions. Responding to those conditions is complicated because it depends on sort of let's say it's not the first order, but second order dependence on the temperature and the low light efficiency. It's going to be most important in the hotter climates where the temperature has a bigger effect. And although it may be a relatively small effect on the order of, let's say 3 to 6% for cad telluride and some of the more advanced silicon technologies, if that's the distinguishing factor, that can give the edge to one technology over another in terms of its LEP, life energy production that Matt mentioned earlier. And in fact, many large installations that are, of thin film cad telluride that are out there in the market right now are showing that some of the cad telluride module installations do in fact have on the order of 5% higher output in a warm climate, where their temperature coefficient is an advantage, and maybe 2 or 3% in cooler climates. Thank you.
Thank you very much, Steve. And if you could advance to the next slide, I'm actually going to leave you with control here because we've had some questions come in. The first two are for you. And again, for the audience, if you would chat your questions to all panelists in the lower right corner in your chat box, there's a send to box that says send to all panelists. You can chat your questions, and I will ask those. The first question that we have is for Steve. What are the range of temperature coefficients for different module technologies, and why are they different?
Okay, it's a good question, and can't answer it in detail in this time, but actually I do have an extra slide here towards the end. This table compares different modules, essentially the major module technologies that are out there right now. The first three are crystalline silicon based, and the last three are the thin film based, and I list the temperature coefficients there. So the standard mono and multicrystalline technology that you see out in the market today has typically a temperature coefficient of, let's say, on the order of minus 0.5% per degree C. Now, some of the more advanced crystalline silicon technologies have temperature coefficients that are on the order of 0.3 or 0.35, as I list there, the HIT cell or the IBC cell. And that's because they've basically eliminated certain loss mechanisms that dominate the standard cell, and what you're left with are ones that have a lower activation energy or lower temperature coefficients. And if you go to the thin film materials, there you have different materials, different absorber layers, they have different band gap optical properties, there are different device structures, there are heterojunctions. So, but you can see that especially the amorphous silicon and cad telluride have temperature coefficients that are on the order of half of your standard mono or multi-silicon. Now, these temperature coefficients depend a little bit on light intensity. Using a single number probably isn't totally the most accurate thing, but it's very good to get a sort of a first level look at those technologies and their temperature difference.
Okay, great, thank you. The second question was also for you. It wanted to know if you could go over again how the flash test power and the field test power was measured.
Okay. I'm wondering if maybe the answer to that isn't here. This is a quote from another paper, and I included it because it was sort of useful. The flash testing means you get each module and you put it on a large area flash simulator that is, designed for the testing modules, and it's typically what the module manufacturers use, but you're measuring each module individually, which means that if that module is being sold to you as a 250-watt module, you might find out that it's 243 or 256 watts. So you're getting the actual initial STC data on each of those modules. The module manufacturers do that, but they typically just, if you just buy them based on their nameplate rating, you lose that finer resolution due to the binning process, where they will group, modules into certain bins. They might be 10 watts wide, they might be 20 watts wide, depending on their manufacturing tolerances. Some module manufacturers are now going to positive only, so they guarantee that the module will only have a positive tolerance. In other words, if they say 250 watts, it'll be between 250 and, let's say, 260 watts or something like that. It won't be anything less than that. So the difference there in that, like in that graph, and I'll go back to it here, the difference between the top and the middle figure is just that difference between using an assumed nameplate rating versus a measured actual rating on each of those modules. That's all.
Okay, and the specific follow-up to the field power was how long was the field power measurement averaged over?
Yes, good. I believe it was averaged over 1 year. I said that there up in the text, field rating over 1 year. And so during that 1 year, a lot of, for example, some of the thin film modules may have degraded, and so their power rating will go down. Just this initial degradation, and so do some silicon cells, modules as well. And so what that means is that after time, the denominator has decreased, and that's what has increased the numerator, or I should say increased the ratio of the energy yield. So during that first year, more realistic operating conditions, maybe the stabilization occurred, and now you're measuring the actual power of that module will have that's much more representative of what its behavior will be for the remaining 19 or 24 years of its life. And so even though the numerator has stayed the same, namely the amount of energy produced over the year or 2 years in this case for that study, they're dividing by a smaller number. Now the bad news is you paid for the initial power rating on that module. So you paid for the, let's say, as a 100-watt module, but if it stabilizes at 95, that may make this ratio look better, but you actually paid for 5 watts of power that you're not getting.
Okay, great. The next question for you, Steve, was, it appears that a lot of your data is based on older modules. Do you think that the improvements in materials of construction and manufacturing technology would lead to a decrease in module performance variances today and next year?
I think that partly, yes, that's going to be true, and especially with the newer technologies like the some of the like the Sanyo hit cells and the thin film modules, where many, in fact, to be very blunt, many of those early studies, the ones that were reported in the late 80s, early 90s, those were modules being produced certainly from what I'd say large pilot scale operations, not certainly the full scale, 100 megawatt type plants or gigawatt plants that we're envisioning now, but from much smaller operations where they may have still been trying to improve their encapsulation or their solder reliability, and that as those procedures improve over time and companies are doing their own reliability study and getting feedback from the field, yes, I believe that those numbers will tighten up, reliability will improve, degradation rates will improve. Yes, the problem is people, it takes several years to get this data, and so, working on a paper earlier this year, the best I could do would be probably, most recent data was maybe from, 2009, 2010.
Okay. I have a couple of questions for Matt, so I'm going to hand control back to Matt Thompson. The first question for Matt was, how is the Principal Solar Institute funded, and by correlation, who is funding the PSI ratings? So, Matt?
Yes, well, the Institute is completely funded by sponsorships. You should visit our webpage, resource guide, for a listing of our sponsors. And you will also find on our webpage a number of very interesting white papers and recordings of past webinars that you probably should enjoy. So please visit us and see, and if you're interested in being a sponsor of Principal Solar Institute, please contact us. Thank you.
And the next question, again, for Matt was, of the 7 criteria that you used to calculate the PSI ratings, were there 1 or 2 that were more important than others, and what's the effect of that? I'll move back to that slide, Matt.
All right, thank you. Well, I believe the strongest lever in our modeled calculation of lifetime energy is the total area efficiency. This is very important. Everybody's concerned about efficiency. If you keep up with the developments in the solar industry, everybody's talking about efficiency. Well, usually they're talking about cell efficiency. I think the important thing for installers, whether it be rooftop or brownfield installers, is the module area efficiency. This is because in the rooftop scenario, of course, there's a limitation to the amount of area on the roof, and so how much energy you can get out is very important. In other situations, commercial and large-scale solar, utility solar scale, for example, the area is still important. Land cost, even in cheap areas, is still high, and there's all sorts of other structures that are associated with larger PV modules, like cabling and support structures. All of these things factor in, and so I think it's completely reasonable to have total area efficiency be related to the module, and it is by far the strongest lever in our computation.
And I'll take one more question before we close up. It was related to the annual power reduction that's shown here. Why are you using the warranty as opposed to using test data or something that the manufacturer provides, even if it's certified?
So the numerical assessment of energy of annual power reduction is very difficult to make, and Stephen, I believe, explained quite clearly how the error bars can dominate the results. And so rather than have our rating plunge into the details of how that annual power rating reduction could be measured, and we use the manufacturer's warranty because we feel like this is tangible. This is something that the manufacturers are willing to stand behind, and therefore we use a linear approach to the annual power reduction number.
Okay, we've run out of time here, so I'll close things. If you have any further questions, you can chat those to the windows, and I'll get those to our panelists. Again, thanks to Steve and to Matt, and thank you also to our sponsor, Principal Solar. And I will put up the abstract that Steve had mentioned in closing, but Steve, you can go ahead and with any parting comments, and Matt as well.
Thanks for the opportunity to letting me discuss this paper, whose abstract is shown there. And if you're interested in more data, you should access it through the Wiley website, and I give the link there.